The statement for the fizzbuzz problem specifies that you need to print integers from 1 to 100. For multiples of 3, instead of the number, you should print fizz. For multiples of 5, instead of printing the number, you should print buzz. And if the number is divisible by both 3 and 5, instead of printing the number, you should print fizzbuzz. It is always a good idea in a coding interview to do a quick run of the expected results without actually writing any code. Here you would discuss that the expected output should be 1, 2, fizz instead of 3, 4, buzz instead of 5, and so on. With this understanding out of the way, we can start writing some code. Let's pick the first requirement. Write a program that prints integers from 1 to 100. We can do that easily with the for loop. We'll terminate the loop right before 101, and we will start the loop at 1. At each step in the loop, we will log out the index. And if we run the application, you can see that it works as expected, printing 1 till 100 inclusive. The next requirement is that for multiples of 3, we should print fizz. We can do that easily with an if-else. If the index is a multiple of 3, we will print out fizz. Else, we will print out the index same as before. And now if you run our application, we can see multiples of 3 getting replaced. The next requirement is that for multiples of 5, we should print buzz. Just another else if to check if it is a multiple of 5, and we log out buzz. And now we are down to the final requirement that for multiples of both 3 and 5, we should print fizzbuzz. Following our previous pattern, you might be tempted to do another else if to check for multiples of 3 and 5 and log out fizzbuzz. However, you should realize that if any of the previous conditions are true, then this combined condition check will never execute. So we simply move this combined condition check to the top. The program specification is intentionally ordered in this way to catch unaware programmers off guard, but fortunately, you will not be one of them. If you run the application, you can see that it is a working solution to the fizzbuzz problem, logging out fizz, buzz, and fizzbuzz as required. A common additional request is to only do the multiple detection math once. It is quite easy to do by simply moving out these fizz and buzz detection expressions and storing their results in semantically named variables isFizz and isBuzz. Next, we simply use these variables instead of using the expressions. Another common additional request is to remove the console log duplication. You can do that by creating a variable for the result and then storing the result in this variable for each condition, and finally logging out the result variable. Another thing the interviewer might request is to remove the mutation of the result variable and present a solution with a more functional approach. They might even give you the hint to use the conditional ternary operator. An if-else chain with only single assignment statements can easily be converted into a ternary chain. We will go ahead and assign the result to an expression driven by the conditional ternary operator. If isFizz and isBuzz, then the expression should evaluate to fizzbuzz. Otherwise, if isFizz, then the expression should evaluate to fizz. And if isBuzz, then the expression should evaluate to buzz. And finally, if none of these conditions were true, it should evaluate back to the index. And then we simply log out the result variable. And now, since there is no lazy assignment to the result variable, we can make it const as well. And the code still functions the same as before. Each array in JavaScript has a sort method specifically designed to sort the array. The sort method will by default sort in ascending order using the string Unicode code points. This works fine for sorting string arrays. For example, if I have an array with foo and bar, if I sort the array, bar will come before foo. There are two big words of caution with the built-in sort method. One is that it mutates the array and returns it. This catches new developers off guard who think that the sort doesn't mutate the original array and only returns a copy. You will sadly find code like this in many beginner-authored JavaScript codebases. Fortunately, with Typescript, you can fix such codebases easily by annotating the array as a read-only array of strings. And now, any mutating methods like the sort method will no longer be allowed on this array. You can now fix it easily by creating a copy of the array using the array prototype slice and then calling sort. And now the original array remains intact when we sort the copied array. The second mode of caution with the built-in sort method is that by default it uses string Unicode code points to sort the items. For example, if we have an array of numbers and we go ahead and sort them, you can see that we get unexpected results. For example, 22 is appearing before 3. Essentially, as far as the comparison behavior is concerned, it is essentially the same as comparing AA with B. And in a dictionary, AA appears before B, and similarly, 22 appears before 3. So whenever you are sorting anything other than strings, you should always pass in a comparer function to the sort method. The comparer function takes any two items within the array and asks you to return a comparison value between the two. If the first value is less than the second value, then you should return a negative number. If the two values are equal, then you should return 0. And if the first value is greater than the second value, then you should return a positive number. For numbers, all of these requirements can be met by simply returning a minus b. And you can see that it works as expected. It is conventional to write the comparer function in its short form. Now that we know how to sort numbers and strings, let's cover how to sort more complex objects. For example, here we have a list of the top movies along with their names and the year in which they were released. I'll go ahead and paste a few other movies as well. We can sort these movies in ascending order of the year in which they were released by simply comparing the two year numbers, as we already know. And now if I go ahead and log out the movies' names, you can see that they are sorted in ascending order of their year of release. To sort the items in descending order, you simply swap the order between the first and the second values in the comparer function. Swapping these in the parameter clues in the code reviewer to your descending order intent. One final thing worth mentioning is that the implementation of the sort algorithm is left open to the implementing runtime. All browsers implement it using algorithms that have an O of n log n average asymptotic runtime. Here we have an array foo of a few strings. The strings contain mixed case, for example alpha with a capital A, beta with a small b, gamma with a capital G, and delta with a small d. By default, if I call the sort method on this array and log out the sorted array, you will see that all the capital words appear before the lowercase ones. Alpha and gamma are before beta and delta. This is because the default string sorting in JavaScript is case sensitive, and capital case strings come before lowercase strings in the Unicode code points. So capital G will come before lowercase b and d. To do case insensitive sorting, we need to provide a custom comparer function to array prototype sort. You simply use a function that takes two strings and uses the locale compare function of the first string to compare the string to the second one and return it. Now there are a few ways of adding case insensitivity to this, but the simplest one with the greatest browser support is to simply convert both strings to lowercase before comparing them using locale compare. And now if you run the code, you can see that the strings are compared case insensitively. Here we have a requirement to determine if two strings are anagrams of each other. For example, earth and heart are anagrams, silent and listen are anagrams, however foo and bar are not. We will start by creating a function called anagrams. It will take two strings s1 and s2 and will return a boolean based on s1 and s2. Now if you try to follow the given definition for an anagram, that is that the arrangement of the characters should match, we could do that by creating a loop over all the permutations of string s1, and for each permutation, if it is equal to the second string, then the two strings are an anagram and we return true. Otherwise, after the loop, we simply return false because the strings are not an anagram. Although such an implementation would work, in this case, the complexity of the algorithm will be equal to the possible permutations of S1, so of an order of n factorial, where n is the number of characters in the string. If you read into the requirements, you can realize that instead of doing actual rearrangements, you simply need to check if they have exactly the same characters. One quick way of checking the equality between two sets of characters in strings is simply to break the strings into their characters, sort them, and then join them again. We do the same for the second string. Finally, we check if the strings are equal. If these sorted character strings are equal, then the original strings were anagrams. The complexity in this case would be driven by the sort function, which is of the order n log n. We can do better. A better way to make sure that the strings have the same characters is simply to use a hash map that counts the characters between the two strings and makes sure that this count per character is the same between the strings. We start by creating a map to track this character count. We initialize it to a map with string keys and number values. We go ahead and iterate through all the characters in string 1. For each character in string 1, we set the character count for this character. We get the previous value for this character. If there was no previous value, we will initialize it to 0. And finally, we increment it to 1. We repeat the process for the second string, iterating through all of its characters. And for each character, if there is not already a key in the character count for this character, then the strings are definitely not anagrams and we can immediately return false. Otherwise, we simply decrement the count for this particular character. Finally, we loop through all the values in the character count map and ensure that every value is 0. This ensures that we saw an equal number of character counts in string 1 during incrementing and string 2 during decrementing. Since we are simply looping through the characters in the two strings and doing a constant amount of work in each iteration, the time complexity of this version is of order n, where n is the number of characters in the strings. Here we have a requirement to determine if a string is a palindrome. We will start by creating our isPalindrome function. It takes a string and returns a boolean, which is true if the string is a palindrome or false if it isn't. To check if a string is a palindrome, we need to check it against its reverse. To get the reverse of a string, we split the string into an array of characters, reverse this array, and finally join back this reversed array into a single string. Now we simply check if the reversed value is equal to the original value and return it. If they are equal, then the string would be a palindrome. A more complex algorithmic challenge commonly presented after isPalindrome is to write a function to check if any permutation of a given string is a palindrome. For example, the word civic is a palindrome. Therefore, any permutation of the same characters, for example, wickik, would also be a palindrome. Similarly, since toot is a palindrome, so is tutu. A non-example would be the characters of the word civil. We start off by creating the isAnyPermutation palindrome function, which will take a string and return a boolean. A simple implementation would be to simply check all the permutations of the string, and if any of those are a palindrome, we would return true. However, in this naive implementation, the runtime complexity will be driven by the permutations function, which is of the order n factorial, where n is the number of characters in the string. We can do better. The insight to a better solution is to realize that a pattern exists among the characters of any palindrome string. Civic is a palindrome as it has C on both sides, followed by an I and an unmatched middle V. The same pattern would hold for any set of characters that can form a palindrome. All characters must be paired off except one, which is allowed to be left unpaired. The characters of civil cannot form a palindrome as both V and L would be unmatched. This reduces our requirement to a simple character pairing problem. We can track character pairing using a simple string set. We split the string into its characters. For each character, if it is in the current unmatched set, then great, we can delete it as it is now matched. If it isn't already there, then we simply add it. Finally, after we have gone through all the characters, we simply check the count of the entries. The characters of a string can form a palindrome if the count of unpaired characters is 0 or 1. This implementation simply loops through the characters of a string and does a linear amount of work in each iteration. Therefore, its runtime is of the order n, where n is the number of characters in the string. First, we will go ahead and create a simple sorting function that explains the concept of bubble sort. The function takes an array of numbers as an argument and will return a sorted array of numbers. Within the function, we create a copy of the original array using slice, and then we return this array. Before returning it, we will sort it using bubble sort. Bubble sort works by looping over the input array n times. In each iteration, the goal is to bubble the highest ranking value to the end. So we loop through all the items in the array, and we simply check if the current value on the left is greater than the current value on the right. If so, we swap the variables at the two positions. This ensures that we keep bubbling the highest value to the last position of the array. Since we are looking up the j+1th item, it makes obvious sense to terminate the inner loop one before the last index. To demonstrate this bubbling of the highest value, let's run through a simple example. We will sort the array 4, 3, 2, 1. We expect the final result to be 1, 2, 3, 4. Within the function, we will log out the original array, and we will also log out the array whenever we do a swap. Now if we run this, you can see that 4 is bubbling to the end, and then 3 is bubbling to the second last position, and finally 2 gets bubbled to the second position. This explains the concept of bubble sort and how it gets its name. Note that instead of always iterating n times, we can easily optimize the algorithm to terminate early. Let's duplicate the function to present a more idiomatic bubble sort implementation. We get rid of this always n time iterating outer loop. We create a variable to track if any bubbling takes place, and we note it down whenever we swap a variable, and break out of the loop once no more swapping is needed. Finally, we wrap the whole thing in a while loop that will terminate if no variable bubbling happens in an iteration. This implementation is similar to the previous one with the simple addition of early termination. This also explains the main real-world use case of bubble sort, which is if you only have a few values that need to be swapped around, bubble sort can be pretty fast. In the worst case, this whole inner for loop of n iterations will run O of n times, resulting in time complexity of O of n squared. Since we are doing the array swaps in place, the space complexity is O of n. We start off by creating a function that takes an array of numbers and will return a sorted array of numbers. Within the function, we create a copy of the original array using slice, and we will return this new array after sorting it in place using a partition subroutine. We kick off this recursive routine by passing in the array, a 0 for the start index, and the array length for the end index. Now let's go ahead and write this partitioning function. It will take an array, the start index of an array section that it needs to partition, and the upper limit of the index for the partitioning. Since it modifies the array in place, it doesn't need to return anything. The Quicksort algorithm is also called partition sort because of this partitioning routine. The partitioning routine is recursive, and like any recursive function, it will have a base case that terminates the recursion. For sorting, you can abort if the length of the partition is less than or equal to 1, as an array of one item is already sorted. The objective in each recursive iteration is to select a pivot element and move the items in the array such that the array satisfies the following property. Items less than the pivot appear before the pivot, and items greater than the pivot appear after the pivot. The Quicksort algorithm is also called pivot sort due to this partitioning around the pivot. There are a few ways to select the pivot. We just go ahead and select a random index from the array subsection that was passed in. To make the remaining algorithm easier, we move the item at this index to the start of the array. This way, we don't need to keep moving the pivot to its rightful place when we are iterating through the elements in the array. The first element of the array is our pivot. We start off by assuming that it is already in its rightful place in the array and store that as the pivot rank. We will loop through the items in the array, maintaining the following invariant. Items less than the pivot appear before the index for the pivot rank, followed by items greater than the pivot, followed by the index for the current item, followed by the remaining items that have yet to be seen. Now let's loop through the array subsection with these invariants in mind. We end the loop before the index reaches the before point. We start the index at start plus 1 as our pivot is at the start position. If the item at the current index is less than the pivot, then we increase the pivot rank, slide the smaller item into the section of the array that holds items less than the pivot. We can do this sliding by simply moving the item at the pivot rank to the current index. This is because the item at this incremented pivot rank should be greater than the pivot. After this sliding, the item at the pivot rank is again smaller than the pivot, which is one of the invariants that we are maintaining. If the item is greater than the pivot, then we just keep on looping without any changes to pivot rank. By the time the loop terminates, we have met our invariant, except that now there are no more new items to see. Now we need to move the pivot to be between the items that are less than and greater than. If the pivot rank didn't change in the loop, then the pivot is already in its rightful place at the start of the array subsection. If the pivot rank did change during our loop, We can simply put the pivot in its rightful place by swapping it with the element at the current pivot rank. This is because any item at the pivot rank is definitely smaller than pivot because of our swaps within the loop. After putting the pivot at its rightful place, the array subsection has been partitioned into items that are less than pivot, followed by the pivot, followed by items that are greater than the pivot. Notice that in each call to partition, not only are we putting the pivot in its rightful place, but more importantly, we are dividing the problem into two smaller problems that can be tackled independently. Items less than the pivot can be sorted independent of the items that are greater than the pivot. We can do this sorting by recursively calling the partition routine on the items less than and items greater than the pivot. The reason why the algorithm is named Quick is because of its very low memory overhead, since we are doing the partitioning in place one by one. At a high level, randomly selecting a pivot gives us a pivot that is in the 25 to 75% rank in a given set of elements at about half the times. This gives us a fairly consistent decreasing problem size, which brings Quicksort's average runtime to O of n log n, similar to merge sort. We will go ahead and create a function for insertion sort that takes a number array and returns a sorted number array. Before we begin, we create a copy of the original array using slice. We will return this array after sorting it in place. The basic idea of insertion sort is to mentally divide the array into a sorted left section and an unsorted right section. We will move an item one by one from the unsorted right section into its rightful place in the sorted left section. The code follows a similar pattern. We loop through all the items in the array, skipping the first one as a single item is already sorted. We will select the current array item and store it in the current variable. Storing the item in a variable opens up a hole at the ith position in the array that we can use to slide items one by one if they are bigger than the current item. We will use j to keep track of which item we are comparing against the current item. We will continue to do comparisons till we arrive at the head of the array, or the item at the jth position is no longer smaller than the current item. Within the loop, we will keep on sliding the item at the jth position to the right, that is the j plus 1th position. Then we continue the loop to test against the next jth index. Once the loop terminates, j is either less than 0, that is, we have fallen off the start of the array, or it means that the item at j is smaller than the current item. In both these cases, we should put the current item at the j plus 1th position. Once the outer loop completes, our sorted left section is equal to the whole array and each item has been placed into its rightful place on the left. Therefore, the whole array is sorted. To understand the algorithm a bit better, let's look at an example. We will sort the array 4, 3, 2, 1. We expect the final result to be 1, 2, 3, 4. We will log out the array before sorting and after sorting. We will also log out the left section of the array we keep sorted and the current item we are going to place into that sorted subsection. You can see that we start with the single sorted item of 4 and we put 3 into its rightful place. Next we move 2 into its rightful place, and finally the current item of 1 into its rightful place to give us the sorted array. The algorithm is called insertion sort because we insert the current item one by one to its rightful place in the sorted subsection of the array. I'll go ahead and delete the log statements now. In different iterations, for the worst case, the inner loop will run as many times as the length of the left array section. So the overall time complexity of the algorithm can be represented by the summation 1, 2, 3 up till n minus 1. If it went all the way up till n, it becomes a fairly familiar summation that a result of n star n minus 1 divided by 2, or O of n squared. Since we are doing the array item moves in place, the space complexity is O of n. We will go ahead and create a function to sort using merge sort. It takes a number array as an argument and returns a sorted number array as its result. Merge sort is a recursive algorithm. In any recursive algorithm, you will have some base conditions that terminate the recursion. For sorting, you can abort if the length of the array is less than or equal to 1, as an array of one item is already sorted. In merge sort, we divide the array into two equal portions and sort them recursively. To get these two portions of the array, we first find the middle index by dividing the array length by 2. We then make two equal slices of the array using array.slice and store them as left and right. For an uneven array length, the right portion will be bigger than the left one, but it shouldn't matter for us as it will all recursively boil down to an array of length 1. We will offload the segment sorting problem recursively to merge sort itself by invoking it with left and right arrays. Finally, we will call the merge function, which will merge these sorted segments into a bigger sorted segment. Let's go ahead and write this merge function. The merge function plays the conquering role in the merge sort divide and conquer algorithm and is truly where the beating heart of merge sort exists. It takes the sorted left and right segments and is responsible for cleverly merging them into a single sorted array. We go ahead and create the array that will contain the merged result. The innovation is to simply one by one select the smallest item from either the left or the right segment and put that into the result, giving us the merged sorted array. We use two variables to track the index into the left and the right segments, L-index for the left segment and R-index for the right segment. We will loop through all the items in the left and the right segments and abort once we are out of elements in both segments. We store the current left and right item lookups into L item and R item to make the remaining loop logic a bit simpler. If we are out of items in the left segment, as indicated by an undefined lookup result, then we should get the next item from the right segment and increment its index. Else, if we are out of items in the right segment, we simply get the next item from the left segment and increment its index. Else, since we have both left and right items, we simply check which one is bigger. If the left item is less than the right item, we add the left item to the array and increment that index. Otherwise, we add the right item as it is smaller and increment the right index. Once the loop terminates, we should have all the items from the left and the right added one by one into the final array, which represents a sorted merged version of left and right. To understand the algorithm, let's run through a simple example. We will call merge sort with the array 4, 3, 2, 1. We expect the output to be 1, 2, 3, 4. We will log out the output of the merge routines input left and right along with the merge result array. We will also log out the input array whenever merge sort is called. This will help us see the recursion on bigger problems going down to smaller subsets. Now let's run this example and get the output. You can see that we split 4, 3, 2, 1 into two smaller problems. The first one is 4, 3, which we further split into 4 and 3. We merge these single item sorted arrays to get the larger sorted array 3, 4. We then do the same for 2, 1, splitting it into 2 and 1 and then merging it as the sorted 1, 2. Finally, we merge these 3, 4, 1, 2 into the sorted 1, 2, 3, 4. This is our final merged output. The time cost for the recursive work in merge sort can be shown as an equation. We have two recursive calls to merge sort itself, each half the size of the original problem. We then do a linear amount of work in the merge function, simply looping over the items in the left and the right segments once. Therefore, t of n is equal to 2 times t of n by 2 along with the linear amount of work within the merge function. If you solve this recursion by induction, you get an approximate upper bound runtime of O of n log n. We start off by creating a binary search function. This function takes an array of numbers and an element that we have to find within this array. The function will return the index of the element if it is found within the array. If we do not find the element within the array, we will simply return -1. Now to search for the element, one way to do that is to simply loop through all the elements in the array till some element matches the element that we are searching for. If it matches, we return the index. In the worst case, the time complexity of this algorithm is O of n, since we have to access all the elements of the array. If we were to use the simple array prototype findIndex function, it would internally do a similar loop over all the elements of the array, and its time complexity will also be O of n. We can do better than this O of n runtime. These simple loop-based implementations fail to take advantage of the fact that the given array is sorted. In binary search, we recursively break down the problem into smaller ones. We will only search for the element within a given start and end range of the array. We initialize this range to be the entire array. Like all converging recursive algorithms, we will have a base case to terminate the recursion. For search, we can terminate if the problem space has gone below 0. In this case, we have not found our element yet, and we can return -1. Next, we simply divide the current problem space into two equal search spaces by finding the middle element of the current search subsection. If the middle element matches the element we are searching for, we have found our index, which is simply the middle. Else, we check if the element that we have to find is less than the middle element. If so, we recurse through the first half of the problem space, as the element, if present, will have to be in that section. Otherwise, if the element is greater than the middle element, we recurse through the second half of the problem space. And that's it. This algorithm is called binary search because we divide the search problem into two, that is, binary subproblems. Since in each recursive call we break down the search space in half, our problem size decreases exponentially, taking our worst case time complexity from O of n to O of log n. We start off by creating a function which takes an array of type t items and returns a repeated item, if any. Within the function, we will throw an error if no item repetition is found. Intuitively, we can check item repetition by iterating through all the items of the array one by one, and for each item, checking it against any items that appear further in the array. So we'll start the second iteration from i+1. If the current item and some item on the right of it matches, we have found a duplicate and we can return it. This implementation does work fine. However, due to the two loops, the worst case runtime is of the order n squared when n is the length of the array. We can do better by using a data structure designed for checking object uniqueness. Obviously, we are going to use a set. We start off by creating a set for items of type T. We loop through each item in the array. If an item with the same value already exists in the set, we have found a duplicate and we return it. Otherwise, we add this item to the set and continue. Once the loop completes, we throw the same as before. Since we only loop through the items in the array once, doing constant work in each loop thanks to the set data structure, the runtime now falls to the order of n, where n is the length of the array. JavaScript math.random function provides you with a random floating point number in the range 0 inclusive and 1 exclusive. Let's go ahead and loop for 100 times and log out the result for math.random. You can easily scale this 0 to less than 1 result to an upper limit by simple multiplication. For example, if we go ahead and multiply the result with 100, we get random values in the range 0 inclusive all the way up to less than 100. You can limit this value to an integer if you wanted by simply using math.flow. Values in the range 0 to less than 1 get chopped to 0, in the range 1 to less than 2 get chopped to 1, and so on till 99 to less than 100 gets chopped to 99. A common challenge presented to beginning developers in an interview is to go ahead and create a function that should return an integer between a given start and end value. We start off by creating a function that accepts a start value and a before value. We simply add start to the result to make sure that at least start is included. Next, we flow the value returned by math.random after scaling it up to the length of the start before range. As a demonstration, let's go ahead and run this function 100 times, and we can use a different start value if you wanted. A stack is a last in first out data structure with key operations having a time complexity of O of 1. We can model this easily in Typescript using a generic class for items of type T. The stack data structure has two key operations. The first one is push, which adds an item in O of 1. The other key operation pops an item from the stack, again in O of 1. If there are no more items, we can return an out of bound value, for example undefined. This fact can be modeled into the type system by using a union of T and undefined. The objective is to implement these push and pop operations such that they operate in O of 1 time. Fortunately, in JavaScript implementations, array functions that do not require any changes to the index of the current items have an average runtime of O of 1. Therefore, we can simply implement the operations of this data structure using an array. On push, we simply push the new item into the array. As it doesn't change the index of the current items, this is O of 1. Similarly, on pop, we simply pop the last value from the array. Again, it doesn't change the index of the other items in the array, so it is again O of 1. A common additional operation for collection data structures is the size, as it allows you to safely iterate the elements and find out if there are any more elements present in the data structure. Fortunately, JavaScript arrays implement this for us in the form of the length property. A queue is a first in, first out collection data structure with the time complexity of O of 1 for key operations. We can easily model this in Typescript using a generic class for items of type T. Now a queue has two key operations: inQ, which adds an item to the queue in a time complexity of O of 1, and then there is the dequeue operation, which removes the first item that was added to the queue, again in a time complexity of O of 1. If there are no more items in the queue, then it can return something that is out of bound, for example, undefined. Of course, this information can be encoded as a return value for the dequeue method of the queue class. Now we can naively try and implement this data structure using the JavaScript array. For example, we go ahead and store the items internally as an array of type T in a member called Tara, and whenever the inQ operation is called, we simply push the item into this array, and whenever we have to dequeue, we shift out the first item from the array. However, this implementation is incorrect because in JavaScript arrays implementations, shift requires changing the index of any remaining elements in the array. Therefore, this implementation has an average runtime of O of n and thus does not meet our O of 1 operation cost requirement. Not all is lost though, because we can implement a queue by internally using a map. Here we simply use a null prototype object as a map. With this map, we will need to track the valid range of indexes in the form of the last dequeued index as well as the next inQ index. Both of these we initialize to 0. Whenever we need to inQ a new item, we will store the item at the current next inQ index within the internal data map, followed by incrementing the next inQ index for any future calls to inQ. Now whenever there is a call to dequeue, we simply check if the last dequeued index hasn't caught up to the next inQ index. If it has, then we let the default return of undefined handle that scenario. Otherwise, we load the item that we plan to dequeue from the internal data map. We then delete it from the internal map to conserve space. Next, we increment our last dequeued index for any future calls to dequeue, and finally return this dequeued item. In short, the implementation is simply maintaining a map and tracking our queue and dequeue indexes within the inQ and dequeue methods. Now the common additional requirement of adding a size function, which returns the number of elements in the queue, can easily be met by diffing the next inQ index with the last dequeued index. A linked list is simply a list of nodes. Each node has a value and a link to the next node in the list, till we arrive at the end of the list where next will be undefined. The linked list data structure itself simply maintains the head node. Now the trick to writing a linked list and really any data structure with the concept of a node, for example a binary tree, is to first define a node. So let's jump into Typescript and define what we mean by a node. We go ahead and create a generic interface for the linked list node. Each node will have a value and an optional pointer to the next node, which will be again a linked list node. Now let's go ahead and model the linked list as a generic class for values of type T. Now all that we really need to do is to store a reference to the head. Although this class can be considered complete, it puts the burden of doing safe manipulation of next pointers on the users of this class. We can easily provide our users a utility add method that lets them add an item to the linked list. To make it easy for us to add an item in O of 1 runtime, we should track the current tail of the linked list. So we go ahead and add a member for that. Now we go ahead and create the add method. It simply takes a value of type t. We go ahead and create a new linked list node with the given value. This node will be our new tail. Now if this is the first node that we are seeing, we will also initialize the head. Additionally, if we already have the tail node, its next pointer should be updated to this new node. And finally, we set this new node as our current tail. Great. So now our users can easily and safely add items to the linked list. As an added convenience to our users, we can also provide a method that generates an iterator over all the values in the list. We simply start at the head, which demonstrates a good reason to have a reference to the head. And within a while loop, as long as we have a current item, we simply yield its value. Finally, we update our current to the next value, which may or may not be there. Now let's go ahead and demonstrate this function in action. We go ahead and create a linked list of numbers. We add a few numbers to the list. Next, we simply iterate over the values from the linked list and log them out. Now if you go ahead and demo the file, you can see that the values returned from the list match what we added. Now as a final exercise, we can easily add a first in first out dequeue operation to the linked list, which also operates in O of 1. We go ahead and add a method to the class. The method will simply return either a value or undefined if we are out of values. We will only return a value while we still have a valid head reference. We grab the value from our head, update our head to be the next value. If our new head is undefined, it means we will be out of items after this dequeue operation and should update our tail to match. Finally, with our maintenance of head and tail out of the way, we simply return the retrieved value. This example demonstrates the real beauty of a linked list. Any operation that only requires a constant number of next reference manipulations can be implemented in such a way to have O of 1 runtime. Here we have a single linked list with a first in first out dequeue method. Now let's go ahead and add a last in first out pop operation. Like dequeue, it will return t or undefined. We only care if we have a tail, and we load the value from the current tail. Now we have to update the tail to be the second last item in the linked list. To find that in this singly linked list, we would need to start from the head till we arrive at the node whose next is the current tail. However, such an implementation would be O of n, and we want an O of 1 algorithm for the pop method. There is a data structure called a doubly linked list that would make it trivial to figure out the second last node, that is, the node previous to the current tail. Instead of just value and next, we also keep track of any previous node against each node. Of course, for the head, the previous will be undefined, and for the tail, next will be undefined. Let's make this node description concrete and define a doubly linked list node. We're going to declare it as a generic interface that holds a value and potentially the next as well as the previous nodes. We will have to add a very slight additional maintenance for this new prev node reference. On add, we will create a doubly linked list node and therefore also initialize the previous value to be undefined when we create this new node. Additionally, if we have a current tail, we continue to update the next pointer. But now we also update the previous pointer for this new node. The modifications to the dequeue operation are equally simple. After dequeuing the current head, if we get a new head value, we simply need to clear the previous reference. Now with these simple modifications in place, Let's revisit adding a last in first out pop operation. After grabbing the value from the current tail, we simply update the tail to point to the current tail's previous node. If the tail will be no more, we also clear the head. Otherwise, we update this new tail to have no next, essentially popping the old tail. Finally, we return the value we read from the old tail. It is worth mentioning that as long as you understand what a node means in your data structure and appreciate the fact that you need to maintain value previous and next members, you don't need to memorize the code bodies. An interesting fact in this doubly linked list is that our pop method is actually a straight copy of the DQ operation with a simple change of head to tail, previous to next, and next to previous. The main advantage of using a doubly linked list is that any operations that require constant next and prev reference manipulations can be implemented with O of 1 time complexity. In this example, it allowed us to implement a FIFO queue and a LIFO stack operation in a single data structure with an O of 1 time complexity. A common interview question is to write a function that takes a string, parses it, and returns its integer value. For example, the string 123 to its integer value 123. We start by creating our a to I function that takes a string and returns a number. Now JavaScript has a function called parseInt that can do this integer parsing for us. Let's run through a few examples of this built-in function's behavior. For simple ints, we get an int. For ints with a negative sign, we get a negative int. When it encounters a character that is not a numeral, it ignores it and all succeeding characters. It still returns the integer value passed up to that point, so for -123 extra, we still get -123. You can use this fact to easily ignore decimal portions, as demonstrated in this example. Finally, if a string does not start with the decimal numeral, it returns nan, that is, not a number. If you go ahead and run the example, the output matches our expectations. Note that you can customize the behavior of parseInt quite easily by wrapping it in a function. For example, parseInt silently ignoring invalid trailing characters can be considered a behavior you want to change. So, you can easily implement a more fit-for-purpose function with a simple regex test that only allows strings containing things that we support. For example, a leading sign followed by any number of decimal digits. In all other cases, we'll return nan. And now all imperfect inputs to our function will return nan, and we can even verify this by running our example. With practical JavaScript training out of the way, when this question is commonly asked, the interviewer might specify that you are not allowed to use parseInt or any other built-in number passing functionality. They essentially want to see if you can write a function that is similar to how parseInt would be implemented internally. First, we note down the corrector point for 0. This will allow us to convert each decimal digit from a string to its number value. The next thing we need to do is to pass out the sign. We can store this in the sign multiplier. Next, we create an accumulator for the integer result of passing the digits. We go through the string left to right. At each point, we update the accumulator as the sum of the current accumulator multiplied by 10 and the number value of the current character, which we get from its distance from the 0 code. Finally, we return the accumulator multiplied by the sign. If you run through the example with valid inputs, you see that it works as expected. This answer shows your understanding of basic math, like the fact that digits represent powers of 10. The solution also shows an understanding of the fact that string digits represent code points that can be diffed to get their integer representation. The interviewer might additionally ask you about things that can go wrong in this implementation. A good one worth mentioning is that we are assuming that the string only has valid digits. They might then ask you to fix that issue, and you can simply check the result of this difference to be in the range 0 to 9. The key property of a perfect shuffle is that each item should have an equal probability to end up in any index. That is, for n positions, each item should have an 1 over n probability for any given position. Before we jump into code, let's run through an example of the algorithm that we are going to implement. Let's say we have items A, B, C, D, E. The algorithm is simply going to pick a random item, put it in position 0, then pick any of the remaining items and put that in position 1, and then pick any of the remaining items and put that in position 2, and so on till we have shuffled all the items. It is actually very easy to do mathematical analysis of this algorithm and prove its correctness. Let's say we have n items to shuffle. If we randomly pick an element and move it to position 0, it will imply that each item has an equal 1 over n probability of being in position 0. Now the probability of an element making its way to position 1 is equal to the probability of it not making its way to the position 0, which is n minus 1 over n, times the probability of making its way into position 1, which is 1 over the remaining n minus 1 items. The n minus 1s cancel each other out nicely, giving us a probability of 1 over n for the item to appear in position 1. Similarly, for position 2, the probability is n minus 1 over n for having skipped position 0, n minus 2 over n minus 1 for having skipped position 1, and 1 over n minus 2 for having made it into position 2. And once again, all that we are left with after multiplication is 1 over n. This process continues for all the remaining positions, giving us a uniform 1 over n probability for an item to appear in any given position. With mathematical analysis out of the way, let's discuss a bit of the pseudocode for the algorithm. We start off with our input array having an empty shuffle portion and a full unshuffled portion. We then loop through the elements of the array. In each iteration I, we simply put a random item from the unshuffled portion into the ith position within the shuffled portion, hence increasing the length of the shuffled portion. This way, we eventually end up with a fully shuffled array. Now let's implement this algorithm using Typescript. We start by bringing in our randomInt function from a previous lesson. We then go ahead and create a function which takes an array of type t and returns an array of type t. Within the function body, we go ahead and make a copy of the array. Note that if we don't do this, the algorithm can and will essentially operate in place. Next, we simply loop through the input array. In each iteration, we randomly pick an index from any of the remaining unshuffled items. We then swap, putting the randomly chosen item into the array's ith position. And finally, after the loop, we return the shuffled array. Shuffling is one of those algorithms where the correct answer is blindingly simple if you have done it before. What we implemented here is called the modern version of the Fisher-Yates shuffle. Since it only loops through the array once, it operates in linear time, that is, has O of n time complexity. Here we have a graph of nodes A, B, C, D, E. It is nice to have a mental model of a heap as a complete binary tree. The tree would satisfy the heap property if A is less than its children B and C. Similarly, B is less than its children D and E. Note that if the heap property is satisfied for direct children, it is automatically satisfied for any indirect children. For example, A is less than D and A is less than E. If the heap property is satisfied by each parent, it implies that the smallest item in the tree has to be the root node. The heap data structure is called a heap because it has this heap property. Also worth mentioning is the fact that since it is a complete binary tree, the maximum number of levels will be of the order log n, where n is the number of items in the tree. Note that a given set of values can be arranged in multiple ways to satisfy the heap property. For example, given the numbers 4, 4, 5, 6, 9, we can have the following two trees. Both are perfectly valid as each node is smaller than all of its children. The only position that is guaranteed to be the same among all possible heaps with a given set of values is the root node. The root will always be the item with the smallest value. Even though it's nice to have a mental model of a heap as a complete binary tree with pointers, they are normally implemented as an array. An array provides very low memory overhead, and the left and right child nodes can be calculated quite easily. Consider this simple array of indexes 0 to 13. It can be conceptualized as a tree with indexes corresponding to the items of the array. When we are done with the left and right nodes at any given level, we start a new level, and consider these indexes as the left and right of the items of the previous level. We stop whenever we run out of items in the array. Given a node at index n, let's try and figure out a formula to find the index for its left child node. As always, it's a great idea to write down a few examples so we can use these to test our formula. The left node of the 0th index is 1, the left node of the first index is 3, the left node of the third index is 7. The key realization for the formula is that for an item at index n, we will essentially have to skip n spaces on its right and one more to arrive at its left node. So we arrive at the formula for left of n as simply 2n plus 1. Our examples are all satisfied by this formula. Now the right child node is simply 1 plus the left node, so its formula would be 2n plus 2. Not only can we traverse the children of such a binary tree by simple math, we can also traverse the parent of a given index simply by going back from our left and right formulas. We start off with different parent formulas for left and right children. From 2n plus 1, we can see that the left node indexes must be an odd number, and 2n plus 2 means that right node indexes must be an even number. So at a given index, if it is even, we use the parent right formula, otherwise we use the parent left formula. With these left, right and parent equations, we can easily traverse this array-backed binary tree without needing to have pointers. This usage of an array as the backing storage is one of the reasons why heaps are extremely popular. Furthermore, pointer traversal can be done with simple math, which can be done very efficiently with bit shifting tricks for powers of 2. We now have enough context to jump into the implementation of the heap's excellent O of log n add and extract root methods. These are the raison d'etre of the heap data structure. To allow us to compare two items of type t, we need a compare function. This compare function will follow the same semantics as offered by the built-in JavaScript arrays sort method. We start off by creating a generic class for a heap for items of type t. We create a backing data storage as an array for items of type t. We have a constructor that accepts a compare function for items of type t. And then we go ahead and write our private node traversal functions. One for the left child node, one for the right child node, and finally a traversal to the parent from a given node index, which has different implementation depending on the index being even or odd, as we discussed before. Now let's go ahead and create our add method that adds a given element into the heap in O of log n. It takes a new item of type T, and we just go ahead and add the item to the end of the array. As soon as we do that, there may be a violation of the heap property between this new node and its parent. So we will go ahead and add a shift up operation that makes sure that the smallest node rises to the top of the heap again. Within the shift up operation, we simply load the parent, and in each iteration we check if the item at the given index is smaller than its parent. We simply swap the item with its parent, restoring the heap property. In the next iteration, we check this new item against its parent. The loop terminates when the item is no longer violating the heap property with respect to its parent, or we reach the top, in which case the item becomes the new root. Since we only traverse the depth of the tree with the shift up operation, its runtime complexity will be log n, and therefore the add operation will also have a runtime complexity of log n. The other key operation of the heap is the extract root method, which retrieves and removes the root element of the heap in log n. The root element will be the smallest element in the heap for a min heap. Of course, we can only remove an item if there are any items, therefore the method might return undefined. We check if there are any items in the array. If there are, we fetch the root. If we remove this root item, there will be a hole in the head of the internal array. The best way to really fill this hole is with the last item in the array. That would result in the minimum number of array index changes. Now, if the array still contains any items, we move this last item to the head of the array, and then, just like add, we might have an inconsistency that the new root, which we blindly fetched from the end of the array, might be larger than one of its children. This would violate the heap property. We fix this inconsistency by moving it down using a shift down routine. Finally, we would return the root. Now let's create this shift down routine. The main objective is to move the biggest value of the triangle parent left right down to remove a heap violation. We will use a utility min-index method which simply returns the index that contains the smaller value among a given left right. If the right child index is out of range, we check if the left child index is still in range. If not, we return -1 to signal the end. Otherwise, we return the left child index. Else, we simply compare the left and the right child index values and return whichever one is smaller. We kick off by comparing the left and the right nodes of the input index. At each point, we switch the current node with the smaller of its two children. This ensures that the new parent will be the smallest in the current parent left-right triangle. We simply continue till the heap violation is removed, that is, the parent is smaller than its children, or we reach the leaves, in which case there are no children and therefore no more heap violation. Again, the maximum amount of work will be equal to the depth of the tree, which is of the order log n. As a final exercise, we can add a size method like we do for many of our other data structures. In this case, we can simply return the length of the underlying array. Another useful method to have is peek, which instead of removing the item only looks at its value. We can do that quite easily by simply returning the item at the 0th index. Now let's look at an example of this data structure in action. We go ahead and create a heap of numbers, passing in an ascending order comparison function. We add in a few numbers in some random order. Now at this point, the size of the heap should be 3. And if you go ahead and run the demo, it works as expected. Now we can extract the root value one by one from the min heap. We simply go ahead and call the extract root method a few times, and the numbers come out in ascending order. If you run the demo, it works as expected. Worth mentioning is the fact that a heap can easily be changed into a max heap by simply changing the order of arguments in the comparison function. And now, when we extract the root, it should come out in descending order. There are quite a few use cases where this O of log n insertion and extract can greatly improve the efficiency of simple programming challenges. Basically, whenever you see an algorithm requiring repeated minimum or maximum computations, consider using a heap. Consider a perfectly balanced binary tree. In such a tree, we never add items to a new level until all the positions in the previous level are filled up. We can easily and intuitively determine the number of items at any given level as a power of 2. Level 0 has only 1 item, level 1 has 2 items, and level 2 has 4 items, and so on. Now the total number of items in a perfectly balanced binary tree up to level n would simply be the sum of the diverging geometric series where the multiplier is 2. We could use the formula for a diverging geometric series to find the answer to this sum. However, it is not that hard to develop an intuitive understanding for this summation. Let's make a simple table to keep track of the total number of items up to a given level. The 0th level alone has just one node. As a thought experiment, imagine it has 2 items. The first level has 2 items of its own combined with 2 items of a previous level, leading to a total of 4 items. The second level would have twice the items in the previous level, so we would have 4 items of its own, combined with the 4 items of the previous level, resulting in a total of 8 items. Really, at any given level, we have 2 to the power level own items plus 2 to the power level items from the previous level. The only trick for the final summation is that we need to remove the additional 1 we imagined at the 0th level. The level plus 1 variable has a nice name called the height of the tree, leading to the simple formula 2 to the power h minus 1. We can code this up into a JavaScript function quite easily. The function takes a height argument, and we simply return the value based on the formula we just determined. The key takeaway here is really that the number of items that can exist in a balanced binary tree increase exponentially against the height. Similarly, another key fact that should be at the tip of the tongue for an algorithm designer is, given n items placed in a perfectly balanced binary tree, what would be the height? We start off with our derived formula for the max items against a given height. Let's call this n. Swap over the minus 1 to the other side, and we get the max height h by taking log 2 on both sides. Coding up this max height function is just as easy as coding up the max items function. We take the number of items as an argument and return the value as determined by our derived formula. The key takeaway here is that the max height is logarithmic against the number of items n in a balanced binary tree. We use this height is O of log n fact when analyzing algorithms that depend upon the height of a tree, for example, the methods of the heap data structure and binary search trees. Consider the simple array of items 942753. Our task is to sort these in ascending order. We can simplify this task as simple repeated extractions of the minimum item from the set. If we do that, we get the sorted result 2, 3, 4, 5, 7, 9 in ascending order. We already know an amazing data structure called the heap that is great for the specific problem of repeated minimum computations. Let's code up heapsort using the heap data structure. We start off by bringing in the heap class and the compare function from the code we wrote in our heap lesson. Next, we create our heapsort function that takes an array of type t along with the comparison function and simply returns the sorted array. We create a heap based on the passed in comparison function. Next, we push each item into the heap. We prepare the result array, loop n times once more. In each iteration, we extract the root from the heap and put it on the result. Finally, we return the result, and that's it. Let's try it out on our example. We simply console log out the result of heap sorting our example input array. As you can see, it works as expected. Now let's analyze the time complexity of our algorithm. In our code, we loop through the input array, and in each iteration, we simply add the item into the heap, resulting in a time complexity of this section being the complexity of the add operation, which is log n, times the number of iterations, which is n. So in total, n log n. In the second loop, we call extract root n times, so the time complexity is n times the complexity of extract root. So again, the total for this section is n times log n. Therefore, the total complexity of heap sort is of the order n log n. As you can see, simply using the heap data structure has given us the best asymptotic time performance for comparison-based sorting. Assume that you are given numbers slowly one by one. At any point, you can be asked to give the numbers back in ascending order. So the first extraction should give you 2, the second extraction should give you 3, and if I give you another number, you should continue to extract the minimum of the current remaining numbers. We can code this up into a minimum array data structure quite easily and intuitively. We go ahead and create a class for this. We will be storing the data internally in a number array, and whenever you are requested to add an item, we loop through all the existing items and insert it into the array in descending order. Finally, we return, and if all the items existing in the array were larger, we simply push the item at the end. Now, since we might end up looping through all the elements in the array, this add operation has a time complexity of O of n. For extracting the minimum, we now simply need to return the last item in the array, which we can do through the array prototype pop method, which has a time complexity of O of 1. Note that we can simply change this data structure to maintain the maximum value instead of the minimum by simply changing the comparison operation within our add method. So we go ahead and inherit from this class and replace the add method with the new one. Now let's use these classes in a simple sample. We create a minimum array, add some items into it, and iteratively extract the minimum, logging it out at each point. If we go ahead and run this example, you can see that it works as expected, extracting the minimums turn by turn 1, 2, 4, 5. We can also run this example for the maximum by simply changing which data structure we initialize. And again, it works as expected. The complexity of the whole add extract cycle is driven by the complexity of the add operation, which is O of n. Doing this operation for n items results in an O of n squared time complexity, and we can do better. The simple trick here is to remember that there is a data structure designed for the specific problem of repeated minimum or maximum computations. This data structure is called the heap, and we have looked at it in a previous lesson. In fact, the heap data structure is so well suited to this problem that we will not even bother wrapping it in a class. We simply import the heap data structure, initialize it, passing in a comparison function that sorts in ascending order, giving us a min heap. And instead of extract, we now use the heap's extract root method. And when we go ahead and run it, you can see that it works as expected, giving us the repeated minimums 1, 2, 4, 5. The behavior is similar to the minimum array. However, now the add operation is log n, therefore the runtime has gone from n squared to n times log n. As always, we can easily change the behavior to the max heap by swapping the arguments to the comparison function, giving us the same behavior as a maximum array, but with better overall time complexity across the sum of the add and extract operations. Quite commonly in algorithms, you are given items one by one, and the task at hand can easily be solved by looking at all the items you have been given thus far. A classic example of such a task is sorting. Let's say we have some numbers 2, 4, 6, 7, 8, 9. We are not told that they are already sorted and are tasked with sorting them. Of course, we have discussed many excellent algorithms for this, but let's come up with another naive solution. We look at these input numbers one by one, copying them over to their rightful sorted place in an output array. In iteration 1, we get the number 2 and just pop this number into the start. We needed to look at 0 existing numbers. In iteration 2, we pick the next number 4, compare it to 2. Since it's larger, we pop it at the end. In total, we needed to look at 1 existing numbers. In iteration 3, we get the number 6, compare it to 2. Since it's larger, we next compare it to 4. Since it's larger, we now get to pop it at the end. We needed to look at 2 existing numbers. Similarly, in iteration 4, for the worst case, we might need to look at 3 existing items. And so on till iteration n, we might have to look at n-1 existing items. Now the total work across n iterations for this wasteful sorting algorithm is simply the sum of the lookups in each iteration. Let's call this sum A. Another way of writing the same sum is as a descending series, where you continually look at lesser and lesser remaining items till you arrive at 0 remaining items. Now if we just sum these two ways of writing the same equation, we get a new equation where we have n values, all of which are n-1. So 2a equals n times n-1. Thus, the total work A equals n times n-1 divided by 2. You will see this equation quite commonly in textbooks. But as algorithm designers, we are generally interested in the big O complexity, which resolves to the highest power of n, which is n squared. So remember, whenever you are looping n times and looking at all existing items, or looping n times and only decreasing the amount of work in each iteration by 1, the final algorithm will be at least quadratic in nature. Let's first refresh what is a median. The median is the middle element in a sorted list. Given a list of numbers, if we sort them, the median will be the middle element. If we have an even number of elements, we would simply average the middle two elements. The median maintenance problem is also called the continuous median problem. You are given numbers one by one, and at each point you have to find the new median of all the numbers you have seen so far. A naive solution would be to track the numbers internally as a sorted array, and at each new addition put the new number in its rightful place. Let's code this up. We create a class that will maintain the sorted array as data. Then within our add method, we will insert each new item into its sorted position within this data array. The implementation of our add method is very similar to the implementation of the add methods in min and max maintenance algorithms. We simply loop through all the existing items and compare the item against the items at the given index. Finally, once we have the rightful place, we would return the new median. Within the median method, we simply check if the number of items is even. If so, we simply return the average of the two middle elements. If the number of items is odd, then we only need to return the middle element. Since the add method needs to potentially loop through all the existing elements, it takes O of n time. We can do better than that. The trick is similar to what we did for the minimum and maximum maintenance algorithms. This time, we use two heaps instead of one. One to maintain the lower set of elements and one heap to maintain the larger set of elements. The peak method of the smaller max heap will give us the n by 2th smallest element, and peeking into the root of the big item's min heap will give us the n by 2th largest element. The median is simply the value among these two roots. Let's code it up. We start by bringing in our heap data structure that we have written before. We will create a class to maintain these two heaps. We initialize the two heaps, one low max heap for the smaller items, and one high min heap for the larger items. Now we create our add method, which will maintain these two heaps. It takes a new item. If there are no items in the low heap, or the item is smaller than its root, then it belongs in the low heap. Otherwise, we add the item to the high heap. Now the number of items in the two heaps might be imbalanced. We simply determine which of the heaps is bigger, if any. If the difference of size between the two heaps is greater than 1, then we can simply balance them by extracting from the larger heap and putting the item into the smaller heap. Finally, we'll calculate the new median. If the heaps are of equal size, it means we have an even number of elements, and the median is simply the average of the roots of the two heaps. Otherwise, it is the root of the heap that has more elements. And that's it. Since the only complex operations in the add method are not direct calls to our heaps add and extract root methods, we can do this in O of log n time. Let's test our algorithm with a quick example. We start off by creating this new data structure, add a few items, and at each point log out the returned median. We expect the median to be 4, then between 4 and 6 to be 5, and then between 3, 4, and 6 to be 4. As you can see, it works as expected. Given an array of n numbers, we have to return the contiguous subarray that has the largest sum. So for this simple example array, the answer would be the subarray 4 minus 1, 2, 1 with the sum of 6. A naive solution would be to simply check all possible subarrays. That is of the order of O of n square, as we would loop through every starting point, and for every starting point we would check every possible tailing endpoint. We can actually get a much better linear solution with two key observations. First, the maximum sum for any subarray in the range 0 to I, when the element at I must be included, can be represented as the maximum including I minus 1 plus the current value. Of course, if the maximum including I minus 1 is less than 0, there is no point in including that in this sum, and we should only use the value at I. The second observation is that the overall max sum for the subarray 0 to I, irrespective of if the ith item is included or not, can be represented as the larger of the max at I minus 1 or the max of when I is included. Combining these observations, we have these two neatly written down relations. One for the max including I, and one for the overall max at I irrespective of if I is included or not. Notice that up till index I, we know the answer max I immediately if we have the max including I minus 1 and the max of I minus 1. So the answer up till I only depends on values that appear earlier in the array. When a problem can be solved given someone gives us a pre-solved answer to a subset of the problem solving approach is dynamic programming. The optimal answer at I depends on optimal answers for I minus some constant, and the problem is said to have an optimal substructure. A key trait of dynamic programming algorithms is that they can be solved with a simple table. Let's solve the example array by hand to demonstrate this tabular approach. At element minus 2, the maximum including it would be minus 2, so the maximum we can hope to achieve is minus 2. At element 1, the maximum including it would be 1, as there is no point in including the previous minus 2, and the overall maximum is 1. At element minus 3, the maximum forcefully including it would be minus 2, as we should include the previous maximum including of 1. However, since this is less than the previous max, so we wouldn't include max including into the net max. Let's just fill out the rest of the table a bit faster. You basically just follow the two formulas for max inc and max at each step. The sum of the maximum subarray for when all items have been considered is simply the value at the max column for the last row. We could store the table like this in O of n since it is just two additional arrays. Using this table, we could also potentially easily derive the maximum subset array that gave us the final max value. However, we can do better than keeping this full table in memory by keeping track of a few variables. We simply observe that the subset max array would start at index I if the value at I gets copied to the max section. This indicates that this value is greater than any max we had seen so far and essentially starts a new max subarray section. The subset max array would expand to include index I if max including gets copied to the max section, which indicates that this I is in the tail of the max solution. We now have a firm understanding of the problem and we can code it up as a simple iteration from 0 to n. This is another trait of dynamic programming algorithms that you normally use iteration instead of recursion. We start off with a simple function that takes an input array and returns the max contiguous subarray. If we have an empty array, then we go ahead and simply return an empty array. Next, we go ahead and initialize our loop invariants max including max, max start index, and maxed end index. Next, we simply loop through the elements in the array, keeping track of these invariants at each iteration and using their previous values to calculate new ones based on the relations that we have already figured out. Once the loop terminates, we simply return the max contiguous subarray as the slice from the original array using our calculated max start and max end indices. Since this algorithm only does one pass through the input array, it has a linear O of n time complexity and a constant space complexity of O of 1, as we are only maintaining a few variables to track the invariants. Let's go ahead and call the function with the example input array. If we go ahead and run the code, you can see that it works as expected, giving us the maximum contiguous subarray.